Okay, welcome. Thanks for coming to another session of the ICC Colloquium. And this week has turned out to be a remarkable week. We had already on Tuesday a talk on the interface of quantum mechanics and gravity. Professor Robert Wald told us that when we start thinking about black holes, one of the signature effects of general relativity, we are led to think about thermodynamics, and in understanding the thermodynamics to make the connection with quantum mechanics. And we heard a lot of thought experiments about this interface of quantum mechanics and gravity. And today we are going to hear also a different angle on the interface of quantum mechanics and gravity. But the experiments are going to be quite different. They are going to be real experiments, and you can already start to expect from the picture. I don't think the speaker today, Markus Aspelmeyer, has done any experiments with black holes. Perhaps he's tempted to throw, I don't know, the Real Madrid team into a black hole. Imagine. One by one, slowly, finding the maximum painful orbit. But today we are going to hear about quantum tests of gravity, which is, we will hear, is notice that it's not test of quantum gravity. This is a subtle difference that perhaps we will hear about. And the speaker is Markus Aspelmeyer, so let me give a brief introduction. He is currently a professor at the University of Vienna, a member of the Vienna Center for Quantum Science and Technology. He obtained his PhD in 2002 at the LMU University at Munich, and then he moved to as a postdoc to the University of Vienna with the Anton Zeilinger group, and apparently he liked Vienna a lot, and people in Vienna liking him a lot because he stayed there in different categories, climbing up the ladder quite fast. So in 2009, he was already full professor at the University of Vienna. Of course, he has been visiting professor at Caltech and at Harvard and many other places. I don't want to give you the full list of honors and awards because it's quite humbling and, well, but just a highlight, he had the Fresnel Prize in 2007 and the Starting ERC and a Consolator ERC. And Professor Markus Aspelmeyer is, well, saying that it's prolific is correct, but actually it's saying like the Pacific Ocean is wet. It's true, but misses the point. He works in a lot of different things. He's doing many different things. I'll give you a couple of highlights. He's working on precision interferometry and foundations of quantum physics. And I would like to stress especially the line of quantum optomechanics. The idea is use quantum optics to control the motion of particles, microparticles, nanoparticles, increasingly bigger particles, with different goals in mind. Some of these goals are foundations of quantum mechanics, and also, as we will see today, measuring properties of gravity, and also applications to quantum information processing and quantum sensors. Okay, so there are many things he's doing. Actually, when I asked him, do you want to give a colloquium? He said, sure. Can you send me an abstract? Sure. Here is an abstract. Here is another one. Here is another one. 3 abstracts. And I'm sure he's nimble enough to give 3 colloquia in superposition, but I'm not. I said we have to settle for one, so we collapse on this one, quantum test of gravity, and I'll better shut up and let him speak. So please give a warm welcome. Before, just a sec, I always forget this. If you are interested, PhD student, master student, undergrad students, postdocs, if you want to talk to him, remember there is a meeting at 3:30. You can talk physics, you can talk career advice. If you are interested in this kind of physics, where you should go to get a master, PhD, what type of students he's looking for in his group, what type of experiments you would carry in this group on other groups, are there any other groups around in Europe, elsewhere? So any questions you have about physics, career, not football, no soccer, please, let's meet at 3:30 at room 507, okay? Without further ado, let's give a warm welcome to Professor Aspelmeyer.
So to Meo, thank you very much for this very, very too kind introduction. So 2 remarks before I start. In contrast, despite certain rumors that my voice is due to me going out with a couple of postdocs yesterday night and some famous Chilean artists, this is not true. I'm simply having a cold. Although I went out with these guys, And I really have to say I was highly delighted that the Barcelona public was so much supporting Bayern München, despite the unfortunate outcome. But we have next Wednesday for retaliation. So maybe I come to Madrid next Wednesday. Oh, but Barcelona might be better, actually. To my defense, I first sent only one abstract, and then Tomeo said, oh, that might be a little bit too technical, what about... And so then I sent a couple of other alternatives. So we are transitioning from Gedanken experiments to actual experiments. So those of you who already had the pleasure of listening to Bob Wall's talk this week, you will see that now we're going from strongly relativistic regimes into strongly non-relativistic regimes, but still want to see how we can, by combining methods and experiments from quantum physics, learn something about the nature of gravity, and hopefully, and this is where I would like to come to the end, in a regime where the description through purely classical gravity will actually fail. Now, let's get started here. When we think of quantum theory, there's one prominent example, of course, that immediately comes to mind, which is the quantum superposition principle. Quantum superposition principle allows states in nature that cannot be described by the assumption that the system under consideration is in either of two or several well-distinct, sometimes say macroscopically distinct states. In its most extreme version of the superposition principle, this has been formulated in Schrödinger's famous Gedanken experiment, where you can conceive of some evil device, like a quantum system being put in a superposition behind, so for example, a photon behind a beam splitter. So the wave packet of the photon is split, and then if the photon arrives at that arm, then something tragically happens to the cat. If the photon arrives in the other arm, nothing happens. And so we are left in a state where the cat is either alive or not so alive anymore. And actually it was Einstein in a letter to Schrödinger very nicely puts the main message of this type of superposition state. He said, you see, the problem is that by no art of interpretation can this psi function be made an adequate description of the real factual situation. Because he goes on to say that because in reality there is no such thing that is alive and yet not alive at the same time. Now imagine that we replace these two possible states of the cat by two different mass configurations. What is the space-time associated to such a configuration? This is something that I will come back later. So let me start with a brief fact check. Okay? Fact number one, quantum theory works. There's not a single experiment out there in the world of quantum theory that would contradict in any way the predictions of quantum theory. Here's a beautiful example by a colleague of mine at the University of Vienna, the group of Markus Aspelmeyer. They have pioneered matter wave interferometer experiments into the extreme. So they had carbon-60 buckyballs, showed quantum superposition effects with them, a double-slit experiment with massive particles, and here's one of the latest, greatest achievement with a very complex molecule that contains several hundreds of atoms that he actually put through such a grating configuration in a superposition of this molecule being here and over there. And then the interference of those two wave packets again leads to these fantastic fringes, which is really the most prominent proof of the quantum nature of matter in that case. The second fact, GR also works. We have here a beautiful example. I guess everyone here in the audience has already seen now these images, so these data of gravitational signatures of gravitational waves being detected by this large laser interferometer-based detectors, in that case in the US. So if we now basically come up with a list, so here are my examples from quantum theory, and I just pick now the quantum superposition principle and its validity through experiments as one example. We can take many other aspects of quantum theory, but just to show you what experimentally is possible these days or has been done. So we have actually superposition of, for example, orbital angular momentum states of photons with up to a few hundred quantum numbers. We have electrons, so electric current, so where like 1 million electrons are running in a circle, but in a superposition of clockwise and counterclockwise. We have quantum signatures of superpositions of spins, collective spins of up to 10 to the 12 atoms. Well, the macromolecules I already showed you, and nowadays we see quantum signatures that involve collective motions of up to 10 to the 16 atoms. So this is really getting into a regime where we can talk about macroscopic quantum experiments. At the same time, if you look at the experiments on gravity, there's, by the way, a beautiful review article by Clifford Will, if you're interested in that. You can see that modern experiments cover here the full breadth from Earth-based high-precision tests of gravity, like Cavendish-type experiments and others, solar-scale experiments where we are in the weak relativistic regimes but probing at distances of our solar system, up to now really observations in the strong relativistic regimes up to black hole mergers and the dynamics of binary pulsars. So what I would like to do now in this talk is I would like to gradually decrease the gap between these two domains. Yeah? So this is basically our task for today's journey. So here are the three things I would like to talk about. So first I would like to give a very brief and incomplete survey about current experiments where quantum systems are used as test masses to probe classical gravitational fields. Then I would like to pose the question, what if, this is now, I'm falling back to Gedanken experiments, what if the quantum systems that we're using as test masses, what if we can push them in a regime, can make them so heavy that they actually can act as source masses, such that we can probe the gravitational field of a quantum system. So of a system being in some sort of quantum state of matter. And finally, I would like to basically make bridge the gap between a Gedanken experiment and an actual experiment and try to propose a possible way towards realizing such a, you may call it a quantum Cavendish experiment. So let me start with the first part here, quantum systems as test masses. We start by realizing, and again it's more stating it as a fact, that quantum systems are extremely sensitive probes of external fields of any kind. We know magnetic field sensors, electric field sensors, but also for gravity. So one of the pioneering first experiments that probed the interface between quantum physics and gravity was the so-called Cow experiment, after the initials of the authors, Collela, Overhauser, and Werner. So the idea is to probe the influence of Earth's gravitational field on the wave packet dynamics of single neutrons. So in essence, the neutron acquires a dynamical phase when it traverses through the classical gravitational field of the Earth. And in order to probe that, we cannot measure the global phases, but we can measure phase differences. So in order to probe that, you prepare the neutron wave packet in a superposition. You let it go through an interferometer, such that each path acquires a different dynamic phase when it traverses through the apparatus. So by rotating now the apparatus in the Earth's gravitational field, you pick up a phase difference and you induce in the output interference fringes that are due to phase shifts induced by the difference in the gravitational action exerted on the neutron while it traverses this path. Yeah? So what you see here now are gravitationally induced interference fringes on the wave packet dynamics of a neutron. And this is essentially the first experiment which required the use of both Newton's constant and Planck's constant in order to describe interference fringes, for whatever it's worth. So these experiments have been significantly improved in precision ever since. So we are now we are here, you know, in the 70s, and then follow-up experiments in atomic physics actually increased the sensitivity further and further. So in particular by the pioneering works of Markus Aspelmeyer, Steve Chu, and others who introduced actually atomic fountains to probe the effect of Earth's gravitational field. So in this case, it's actually a series of two-photon stimulated Raman processes that creates a sort of Mach-10 type interferometer, so where the atoms are actually, the path of the atoms is actually separated in Earth's gravitational field. And then the phase that an atom accumulates here is actually directly related to the position of the particle at 3 equidistant points in time where you apply this actual Raman processes. And it turns out that 3 points in of a falling body equidistant in time is sufficient to uniquely define the acceleration of the system, and this is why the total phase shift in this interferometer is proportional to the gravitational acceleration. So, and in that case, with these methods, they were able to significantly improve the sensitivity on the acceleration of the atoms through Earth's gravitational acceleration. So just by making this interferometric measurement, so again, you are sensitive now to phase shifts that are imposed because this atom, because the atoms go through 2 different paths and experience 2 different accelerations, and the difference you're actually measuring. So if you look at here at the sensitivities that they get, back in the 90s, this was the very first experiment. The relative precision of measuring Earth's acceleration was on the order of 10 to the minus 6, so 6 digits behind the comma. And over the next 20 years, they basically improved that by another 5 orders of magnitude. And right now, we can measure Earth's acceleration to the 11th digit. And this is data back from 2014. Right now, they have been improving the apparatus, and they basically claim that they can reach another improvement by 3 orders of magnitude. So this is something that is incredibly accelerating in precision, these measurements. What you can also do now is, of course, you can build 2 of these atomic interferometers and at different locations and do a differential acceleration measurement. So you can basically cancel the effect of Earth's gravitational field and just put a mass, another mass here somewhere, for example, a lead mass, like in their case. And now you can measure the actual gravitational attraction of the atoms to the lead mass, which allows you now to measure not directly small g, but big G. So really to measure directly Newton's constant. So it's a completely different way of obtaining directly the coupling constant to the gravitational field. And so 2007, Markus Aspelmeyer's group published the first result with a precision of Newton's constant to 3 digits. And Guglielmo Tino in Florence, they recently published a work where they increased that by another order of magnitude. And the interesting part is here, I will come back to that question later, because it turns out that Newton's constant is the worst determined constant in nature. And this is already getting very close to the best values that have been measured so far. And the interesting part here is that these methods right now are mainly limited by determining the exact position of the atoms. But there you have methods. No? Basically, it's an atom cloud. You can further cool them and so on. So there's a lot of potential to increase this significantly using this atom interferometry techniques. Now, there are other possibilities. Another beautiful example is take a single neutron, right? And we can prepare a neutron in a way that it's really in a very pure state of motion. It can come out of a reactor, we can frequency select it very well. So basically it's described quantum mechanically by a wave packet. It's a very large wave packet actually. Now you let the neutron fall. So it falls on the floor. If the floor is very smooth, you can have a very nicely polished silicon surface, for example. This large neutron now sees all the nuclei of the silicon and is reflected. It just bounces off the nuclei of the atoms in the surface. So it goes back. So what is the potential landscape that the neutron actually sees in such an experiment? Well, think about it. If you plot here the height and here the potential, at 0 heights on the floor, it just hits a wall, right? So infinite potential well. And then while it traverses up in the Earth, it traverses up against the gravitational field. Right? So basically, just linear up. So what the neutron actually sees, it's a box potential. It has a triangular shape, but it's confined. This is a particle in a box. This is quantum mechanics 101. You immediately know what happens. You can immediately quantize the eigenstates here, and you see discrete energy levels for the neutron being at distinct heights above the surface of the Earth. And these experiments have been done. So you can actually directly put a couple of slits. So for example, you have a neutron, it comes out of the reactor, you let it bounce, and then you put a couple of slits afterwards to detect it, and you see that you will only find it in separate heights above the Earth. Now, that means what you have is now a gravitationally bound neutron with energy eigenstates, and the question is now, can you actually access these energies, these energy levels? Think about an atom. So what do we do if we want to learn something about the energy spacing here? We do spectroscopy. We take a laser, we send a laser into the atom, and then we rely on either absorption or fluorescence or whatever, or we do some Rabi oscillations on particular resonance of the atom in order to probe these energy levels. So, question is, what type of laser can we have to drive transitions between these energy levels? So why does a laser work? A laser works for spectroscopy because it creates a little distortion in the potential that the electron actually sees in the atom. Yeah, it's an AC electromagnetic field. It's a time-varying electromagnetic field. It creates a distortion that allows then to drive a transition between the electronic energy states. So we need to create now here a distortion in the trapping potential, in the gravitational field, in order to drive the frequencies, to drive the energy transitions. How do you do that? Well, you just take the floor, so our silicon surface on which the neutrons are reflected, and you shake it. No, just take it, you shake it, because what you do then is you vary the height here of the potential, so you introduce a disturbance to the actual potential, which means if you hit now the frequency times h bar, then you have the energy of this transition, you drive the transitions. And this is actually what people have done. Again, a colleague in Vienna, Hartmut Abele, they have actually implemented this gravity resonance spectroscopy where they can now drive here this different Rabi flops between the energy eigenstates, which is quite, I find it quite sensational, because you now can probe the energy eigenstates of gravitationally bound states of a quantum particle, and it allows you to do also address some other questions. So for example, one of the questions is, and several here in the audience may know that much better than I do, some of the questions related to quantum gravity to some extent is, does Newton's law of gravity hold also for very short distances? There are some expectations coming out of the quantum gravity community that this may not be true. That actually at some finite length scale of a few microns or nanometers, we don't know yet, there is a modification of the 1 over r potential in gravity. So basically nature works different at small distances. Now look at the following. You have here a very small particle with a wave packet size on the order of 100 nanometers. Okay, and the silicon block of which it's reflected has a gravitational potential, generates a gravitational potential on its own. So you can actually now calculate the effect of your experimental part here of this mirror on this potential here. Yeah? So it will be a modification here to this potential. And once you modify this potential, you will modify the energy landscape. So that means measuring here, doing spectroscopy on the energy levels will tell you something about possible modifications on this potential. And because the neutron wave is so small, this is actually the test with the shortest testing the shortest distance so far for gravitational forces at small length scales. And they have a fantastic energy resolution, so they measured that and could bound against some models. Furthermore, it provides some other bounds on, well, pseudoscalar axions. And if you want to know what that is, you ask the left front corner here in the audience. Well, I could go on. There are so many other beautiful examples. Let me just expedite a little bit here. This is from my dear colleague Ernst Rasel in Hanover. They basically managed to take an experiment that creates a Bose-Einstein condensate. And if you ever seen a Bose-Einstein condensate experiment 10 years ago, it would actually fill this whole podium here with optical tables and lasers. And then there would be a little chamber in the middle where the Bose-Einstein condensate is created with 10 to the 6, 10 to the 8 atoms. What they managed to do is to cramp this whole podium of stuff into an 80 centimeter diameter little cylinder, or maybe 2 or 3 of them stacked on top of each other, in such a way that it can fit in this tube, okay? And in such a way that this tube can actually fit into a rocket. And then you build the actual rocket, and then you shoot the rocket up. It's up there like 10 minutes. And during that time, while the rocket is actually up there, you create a BEC, so a Bose-Einstein condensate, using lasers. As I showed you before, you split the atoms such that it builds an interferometer. You let it fall. Everything is free fall now, no? Because the rocket is in free fall. You let it fall, and then you bring it back and make interference. And you basically study atom wave interference in such a 0G environment. Well, ideally later 0G. If you've ever been on such a rocket, I guess you haven't, but that's actually, there's still some little vibrations and there's still atmosphere and so on. So the real goal of this whole thing is to have a dedicated satellite mission where such an atom interferometer, ideally with 2 different species of atoms on board, is going to fly at a Lagrange point where there is no remaining gravitational acceleration whatsoever, and then perform the next generation of high precision tests of the equivalence principle, for example. Because if you have 2 different atomic species, if the equivalence principle doesn't hold, then the phase shift should be different for the different atomic species. Now, let's go a little bit beyond purely Newtonian gravity in a second. Let's talk quickly about gravitational time dilation. So I told you about the Cow experiment, which was the pioneering experiment in neutron interference back in the 70s. Even earlier than that, I think like the starting point of testing gravity with quantum systems was the famous Pound-Repka experiment, which basically measured the frequency shift of a photon due to its location in the gravitational field of the Earth. So basically the photon source up there in Lyman Lab and a 20-meter tower, the photon was spectrally very well defined because it was created in a Mössbauer emission. And then basically it was sent down, and down there it was again caught by another Mössbauer nucleus. And in order to really resonantly hit the frequency again, they had to Doppler shift the detector to compensate actually for the gravitational redshift of the particle. So this was the very first demonstration of this effect. Nowadays, we have atomic clocks. So nowadays we can actually use again the electronic quantum states in atoms. We use some typically either hyperfine splittings of a couple of gigahertz that actually serve as a very stable clock transition. So because this energy is well defined, we have a time that is defined with that. Or we have a rate that is defined with that, so a nice clock. And we can build now optical clocks in the meanwhile with a precision, so with a relative frequency precision on the order of ranging between 10 to the minus 11 and 10 to the minus 18. So the clocks based on microwaves are more in the regime of 10 to the minus 11 or 10 to the minus 13, and modern optical clocks where you use really optical frequencies, they have reached already precisions now up to 10 to the minus 18. So relative frequency precisions. So, which means the following. You can take an optical clock and just monitor its frequency, right? So here, and then you measure the frequency. And then you lift your clock. You know, there's these things that lift your car. I don't know how they are called in English. So you lift it, and you just put it under your optical table, and you lift it there, and the whole thing is lifted. And then just watch how actually the clock changes its frequency. Yeah? While you lift just your optical table with the experiment by 30 centimeters in Earth's gravitational field. Yeah? And this was done 2010. So, so they were sensitive to a 30 centimeter shift in Earth's gravitational field. Nowadays, well, they gained at least 1 order of magnitude, if not even 2. So nowadays you're actually sensitive to 3 millimeters in the Earth's gravitational field. Okay? Which means, by the way, clock synchronization over long distances with the at the precision that we are talking here is becoming a real problem, because you will have to compensate for the gravitational time dilation effects in a network of highly precise clocks. On the other hand, we want highly precise clocks because this is what determines our bandwidth in communication. So if we want high bandwidth communication, then we need to compensate for gravitational time dilation effects in the long run. Yeah? So it's an interesting compromise actually, and you have to communicate that to telecom companies also at some point down the road. So talking about job opportunities for the future, right? So if you want to get a job in telecom, learn your GR. And quantum, obviously, you know, because you also have to know how the atomic clock works. Okay, so well, basically, I guess I will start having to skip a couple of examples. So that's my last one, okay, because it's so nice. So here's my last one. So right now we always considered particles in a superposition and looking at the influence of just the dynamic phase on the wave function of the particle. But what if we add now really GR to the game? Because previously this just you could have done that just with a flat background space. What if we add GR to the game, and instead of having a particle, just the center of mass, we take a clock? Yeah, we basically take an atom with an internal degree of freedom that rotates, so it establishes a clock. So let's take a clock and put a clock in a superposition. What's going to happen? Well, because the clock is in a superposition now, and at one arm of the interferometer, because of time dilation, it will actually go faster or slower than the other. It will arrive here at the end of our interferometer with a difference. So the two clocks are now suddenly distinguishable because of gravitational time dilation, which means your interference, your quantum interference will be gone, or actually will vanish, yeah, because they are out of phase. We wouldn't call it decoherence, we would call it dephasing, because essentially you just accumulate a phase difference that makes this vanish. And it rephases, of course, once you made one full turn, one full 2 pi. Okay? Question is, well, can you actually measure something like that? And the answer is in principle, yes. So if you look at current experiments, and I don't go through the numbers here now, I've written them down. If you're interested, we can talk about that later. The main message is if you combine current know-how that is out there in the world of quantum experiments, for example, Harosh's beautiful experiments with highly excited Rydberg atoms, together with Kasevich's beautiful experiments with extremely largely separated atoms in interferometers, then you should be able to do such an experiment. Really demonstrate that gravitational time dilation can affect directly quantum interference. Okay. Well, I will skip here the rest. There are, well, maybe just as a summary, there are many more opportunities. If you look in the literature, the number of suggestions, what people are doing at the interface between quantum physics and gravity is just an exploding field. So there are experiments by Holger Müller and Ed Heinz and others that try to put constraints on dark energy predictions using atom interferometers. There are people in Italy, for example, who look at low energy consequences of possible quantum gravity scenarios and looking for signatures there, or excluding, by not measuring anything, excluding certain scenarios for quantum theories of gravity. There are beautiful ideas how one can search for quantum gravity effects, like Klaus Lemmerzahl and others. There's a lot of things going on the domain of what is called analog gravity. So we basically take a quantum system that mimics the dynamics of gravitational fields, up to trying to realize black hole horizons and Hawking radiation and so on in a cold atom experiment. There are ideas basically similar to what I just said, so really taking atom interferometers and not only testing Newtonian gravity, but really going into the consequences of GR. There's a lot of stuff going on now with quantum optics experiments on board of satellites. If you followed the news a little bit, there has been a series of quantum satellites being launched, mostly meaning that you had either single photon sources or entangled photon sources on board of satellites that would either distribute then down to Earth and or basically between different receivers. And there are a lot of ideas around how you can make use of such configurations. Okay, so basically this is where we are today. This was a very lengthy introduction, and it's still incomplete into the capabilities of today's quantum experiments to test aspects of gravity. Again, low energy, but both Newtonian and also already non-Newtonian aspects. So now let me ask my question. What I have shown you now is that quantum systems are super test masses. So you can perform experiments such that you are very sensitive to gravitational fields. So can we think about a situation where a quantum system can act as a source mass for gravity? So when we take into account the fact that each object basically also exerts a gravitational force. So here's a Gedanken experiment. This has actually been put forward in that way by Richard Feynman at the very famous Chapel Hill conference in '57. So the idea is the following. You take now a mass. We can think of an atom, but we can also think of larger masses. And you place it by some apparatus in a superposition of being here and here. Yeah? You have a superposition of the object being in two places. So here there's some device, whatever, that does this, Stern-Gerlach type device. So now we create a superposition of this sphere being here or here. And then you have a second object being close, and now you switch on gravity. What's going to happen? Well, according to quantum theory, the answer is relatively simple. You will generate entanglement between the two objects, because you have here a superposition of this object here. So that means you have one branch of your state will exert an acceleration of this sphere in this direction, the other branch in this direction. So it means you will eventually arrive at entanglement in the positions and momenta of these two objects. Okay? So for Feynman, this was a very critical Gedanken experiment. His point for putting that out here was, he said, if you believe in quantum mechanics up to any level, you have to believe in gravitational quantization in order to describe this experiment. That's an interesting quote that well, we have been discussing already all along. But there were more people at this conference. For example, there was Louis Witten, so the father of Ed Witten, and he stood up. Actually, the nice thing on this conference is everything is completely transcribed. So actually, it's a book of the conference, and you have every single discussion of the conference is actually recorded and transcribed. So you can really follow the whole argument there. So Witten stood up and said, "What prevents this from becoming a practical experiment?" And that's exactly the question that I would like to answer now or address for the remaining 15 minutes. Can we do such an experiment? So we can do a simple back-on-the-envelope calculation. I spare you the details, but it's really easy to do. And you can do the following. So you can, let's put some numbers. So we say that these two objects are made out of lead because it's very dense, so you can put a lot of atoms in a small region of space. And we say they are on the order of a few hundred microns. That's super macroscopic for a quantum physicist. So it's as classical as it gets. And it's, of course, super small for a person from gravity research. Okay, so I'm sort of sitting between two chairs now with these numbers. So we assume that for this one object, we can create a superposition of the object being here and displaced by 500 nanometers. So only a tiny bit. We make a super tiny superposition size. Okay? And the other object is placed another few hundred microns away. And we prepare it in a pure state. That's something we know how to do from atomic physics. You trap that particle in a trap and you cool the motional state of the particle down to the ground state of the trap, and then you have a pure state prepared. Okay? As easy as that. And then you just let the whole thing fall. Okay? You just let it fall. So what's going to happen? Well, as I said, the two will become entangled, and you can calculate now how long it's going to take until these two systems become entangled, and you can come up with an entanglement rate. And for these numbers that I gave you, it's on the order of a few hundred milliseconds. That's great. I mean, obviously, I choose the numbers that at the end there will be a few hundred milliseconds, because if there's 10,000 seconds, there's no way. Because it would mean that I would have to have 10,000 seconds of coherent evolution. You can forget about that. A few hundred milliseconds is something, as an experimental physicist, I will continue to look at it. Okay? And there are a couple of additional good messages. What I've done here is this back-on-the-envelope calculation is really the lamest thing you can do, because, well, I'm an experimentalist, so that's what I can do, and so it's the zeroth approximation. But you can do much better. So it turns out Oriol Romero Izard, who graduated from here, as I learned, right? So he proposed recently a way to speed up these rates dramatically, not by not just letting these objects fall, switch everything off, but by dynamically changing the potential that these particles see. So instead of just looking at free evolution, for example, you invert the potential. Yeah? You basically suddenly have a repelling potential instead of no potential at all, and you can boost dramatically the timescales. Or if you stick to the timescales, if you stick to the few hundred milliseconds, you can do it with much smaller particles. So instead of 500 micron particle, you can do it now with a 2 micron particle. And now we start talking. And this is also, again, just a zeroth approximation of looking at, let's say, a very intuitive sequence of things. So I'm pretty sure by applying some additional quantum optimal control schemes, you can push that even more down. Just to note that briefly, there has recently been a refined proposal of this case here. So instead of having one object in a superposition and one in a pure state, they actually look at two objects being in a superposition, and they draw a very nice analogy to a so-called conditional sign shift gate relevant in quantum information. So I think this appeals to a quite large community that now starts to understand these problems much better. Okay, so here's the two questions we have to address now in order to make such an experiment. How small can a source mass be? Because in the end, we need to measure we need to be sensitive in the experiment to the effects of gravity. So we need to be able to isolate gravity as a coupling force in the experiment. How can we do that? Because there are other forces, Coulomb, van der Waals, and so on, Casimir, they will all also come into play. So how small can we do that? And then, of course, how massive can we build a quantum system? That's the second natural question. So I will very quickly walk you through that too. So here's the question: how massive, how small can we go? This is a sort of summary of current state of the art in macroscopic superpositions with respect to position of an object, because we're only talking about that now, putting an object in the superposition of two places. So here's coherence times in experiments, here's mass, and as you can see here, the matter wave experiments I've been talking about before, like for molecules and so on, they have incredible coherence times on the order of seconds, but super small masses. There's no way that these masses can serve as a source mass of sufficient strength. Then there are mechanical quantum systems, I will say something about in a second, where you can dramatically improve on the mass, in many orders of magnitude, but also the coherence time drops down very quickly. Because simply the solid state systems are connected to the environment, they couple strongly to the environment, so coherence is not so nice. And on the gravity side, the interesting part is if you ask what is the smallest mass of which people have so far measured a gravitational field, then it turns out it's 100 grams. It's really surprisingly large. So basically the best Cavendish experiment so far with the smallest source masses that were used in Cavendish type experiments were 100 grams. So our task, and the Feynman-Gedanken experiment is somewhere here, okay? And this is a log-log scale, which makes it really difficult to go into this regime. But as I told you, there are some ideas how to go here and then maybe also how to go here. So I think this can still move a little bit down to this side. But the challenge is clear. The challenge is to bring these two domains together. Okay? This is the task that we set out. Now, I don't bore you now with the details. I give you very quickly here one experiment that we are building right now. We want to see now, to address the first question, we want to see how small can we make a source mass and measure its gravitational field. It turns out if you just miniaturize a Cavendish experiment, so it's a torsional balance with the source masses at the outside, if you just miniaturize that, the moment of inertia of a torsional balance scales extremely unfavorable with size. So if you make it smaller and smaller, it becomes increasingly harder to become sensitive to the gravitational effect. So what we thought is, well, we make use of our knowledge that we gained in micromechanical experiments and basically take a test mass, an harmonic oscillator test mass, that we drive through a modulated gravitational field of a small source mass. So we just here harmonic oscillator, here we put our source mass on a stick and we just shake the stick. And thereby provide a time-dependent gravitational force here at the location of our test mass, and then this thing should bring up. So this is the very, very simple idea. And if you put some numbers, so if you calculate, for example, your signal to noise ratio, so here red is actually the thermal noise as a function of size of the object. So the smaller you get, the larger becomes the thermal noise, so Brownian, the effect of Brownian noise in the system. And here the Newtonian effect, so basically the magnitude of the displacement due to Newton. Of course, the larger you make the system, the larger the force becomes, the smaller you make it smaller. So you try to find now a good regime where the signal to noise ratio is still like 10 or so. And you see that for the simple parameters that we have in for a first experiment, we can go down to a millimeter object size. And that's what we are trying right now. So basically, we're trying to build an experiment at the moment. So we already have some first test mass designs where we have like a 1 millimeter lead sphere on a silicon carbide micromechanical resonator. We are working now on vibration isolation. Is actually the most crucial task. And a good optical readout for reading, basically reaching displacement sensitivities at the thermal noise limit of the motion of such a micromechanical cantilever. Another interesting part here is that if you go to slightly larger masses, then this could become an extremely sensitive test also for measuring big G. simply because the signal to noise, if you go in this direction and make a 10 millimeter sphere or so, the signal to noise is just skyrocketing, and this might provide a completely different way to accessing Newton's constant. And so just to remind you, because I really find that quite funny, this is at the moment really a big problem in the experimental community, that the value of Newton's constants is so ill-defined. So basically what you see here is all the different measurements on big G, and the point is that the precision is increasing, so the size of the error bars is going down and down, but the accuracy is not. So basically the data points are still completely on both sides here of the codata value, and the question is, what is the reason? And one of the reasons is that if you look at the error budgets, many of the errors that are accumulated are actually due to the fact that they operate with large source masses. And large source masses always have density inhomogeneities, and it's very hard to actually find the exact location of the center of mass in a large source mass. And this is a huge error. So if you could go to small source masses, you could reduce this error. You could actually have single crystalline source masses, and so on and so on. So this could be an interesting possibility to go in this direction. So last point, you always sometimes you need to quantify the level of desperateness in a field. And one way of doing it is when people start, let's say, making correlations between data points that you may find curious. So this is a plot that shows the level of desperateness in this community. This is the value of big G plotted against the source masses that were used in the experiments. And there's a very suggestive slope that goes down here. And I thought when I saw this plot, I thought, boy, these guys really are desperate. So that's why I find it an interesting task to basically deliver another data point down here, because this is what our experiment would do, right? It would be somewhere here in the milligram and sub-milligram regime. Okay, so we're getting late. I don't want to take too much of your time. Here's my final answer for how massive can a quantum system be. And this is now where we combine, I would say, the whole domain of quantum technologies with the domain of gravitational research. So the idea for making large quantum systems actually comes from a development that has been taking place over the last 10 years. And this is really more in the domain of quantum engineering, quantum technologies, quantum control, where people tried to prepare mechanical systems in a quantum regimes. And I'm really talking now about solid-state resonators, solid-state nano and micromechanical resonators that are coupled to electromagnetic fields. So essentially through coupling by coupling them through optical or microwave cavities, and using the methods of atomic physics and quantum optics to drive these mechanical degrees of freedom into the quantum regime. And I just give you here the summary. I mean, this would be a complete separate talk. This was the first abstract that I sent. Basically, give you an introduction to this field. So I just give you the summary now. So what people can do now? So it really started approximately 10 years ago that this field took off. And by now we have experiments where we do quantum ground so really laser cooling to quantum ground states of motions of such mechanical oscillator that's now a freestanding nanomechanical waveguide made out of silicon. We can generate squeeze states of motion of such micromechanical objects. We can prepare non-Gaussian quantum states of motion, and we can prepare quantum entanglements between mechanical oscillators, for example. So basically, we are now, after 10 years of research, at a state where we can really manipulate and control quantum states of mechanical motion in the quantum regime. So why is that of relevance to the question of massive systems? Well, because using that technique, we might be able to combine the best of two worlds. Namely, we have solid state mechanical quantum devices now that contain a lot of atoms. So actually we are controlling the center of mass degree of freedom. And that contains an awful lot of atoms, like up to 10 to the 16 atoms, with the problem that the coherence time is very small. Why? Because these stupid mechanical systems, they are clamped somewhere here to an environment, and when you vibrate, then everything goes through the support. Yeah, that's bad. On the other hand, we know the matter wave interferometry experiments, they have incredible coherence times, but too small masses. Why do they have so large coherence times? Well, because they just fly through space unaffected, because they're not connected to anything. So the most simple idea would be, well, just cut the support here and go to levitated systems. Have a solid state object levitated in an external trap, and then do all these control techniques, and then you have a solid state, highly massive object that is in the quantum machine. Okay, so that's the idea. So once you have that, so there are a couple of ideas, so either with optical or mechanical levitations. So for example, you trap your particle here in a trap, and now you see this motion here is now coupled to a cavity field. And essentially the whole atomic physics that comes in now is very simple. If the particle moves here in this cavity field, so this is a resonator, so it scatters photons off the cavity field. And what you get is actually Raman scattering, because it's mechanical motion, so you get elastic scattering processes. And Raman scattering generates these nice Raman sidebands. So Stokes and anti-Stokes scattering creates the sidebands, and you have an optical resonator. That means you can now resonantly enhance one of those two scattering processes, either on this side or on that side, that allows you now to either cool the system or generate entanglement with the radiation field, and so on and so on. So this is the essence of optomechanical quantum control of these systems. And what we are actually doing is we are trying to bring particles now close to such an optical resonator, and then once we have the particle there, switch on the cavity field and establish control. But one can also replace such a cavity. This is now more for the quantum optics affine people in the audience. Instead of having such a Fabry-Perot resonator, you can also take a photonic crystal cavity, so just a solid state resonator. That's also things we are doing, where we basically trap a particle in the vicinity of such a photonic crystal cavity that is basically just attached to an optical fiber, and then we can control the motion of the particle through the interaction with the near field of this photonic crystal cavity. So these are all methods that allow us to achieve quantum control over the motional states of these systems. We are not yet there, so we have experiments, for example, where we trap atoms, trap these particles. These are like 100 nanometer dielectric particles inside optical cavities. So you see here, these are the cavity mirrors, that's the standing wave, and we trap particles here. In this case, we just then give a kick to the optical table, then all of the particles drop out apart from one. So we have a single particle now that can now interact with the cavity field. And if you look here down here, for example, so here's actually the light transmitted through the cavity, and you can see here these sidebands. So these sidebands to the pump laser, to the drive laser of the cavity, these are actually motional sidebands imposed onto the cavity field because of the motion of the particle. These are the Stokes and anti-Stokes scattered components, and with that we can then now do all the physics. Again, we are very close with these experiments. We are close to a regime, the so-called strong cooperativity regime, that is required in atomic physics also to start doing quantum control. That is basically the current status. So once you have prepared such pure states, you then can basically prepare superposition states. There are a couple of protocols that we and others have actually been working on and suggesting, and that allows us then to create these large superpositions and eventually hopefully measure interference with these macroscopic particles. Okay, so I'm essentially at the end. Let me try to summarize here a little bit where this could go. So this would be sort of the ultimate experiment would be to try to generate entanglement through gravitational interaction in a quantum system. And if you look at the time scales here, so in this beautiful paper by the Isard group, you can actually, this is the time that I showed you before on the back on the envelope calculation. How long does it take for the system to become entangled? You can plot here the entanglement time as a function of mass, and you can see as long as you're here with 10 to the 6, 10 to the 8 atoms or so, you have thousands of seconds, even 10,000 of seconds. There's no way you can do such an experiment on Earth. There are proposals actually looking in this regime with 1,000 seconds and nano particles that basically build on existing satellite technology and suggest that you can put such an experiment onto an optical platform like the one that was used now for the LISA Pathfinder experiment, and then perform an experiment at coherence times of 1,000 seconds. So this is ongoing activities with respect to space. But you can also think of increasing the mass even further. So really going to the 2-3 micron regime. You cannot do optical levitation anymore in that case. You need to use, for example, superconductors or magnets and levitate them. But you can also do that. So you can actually levitate superconductors, and you can then couple the motion of a superconductor to superconducting cavities and use microwave radiation to do quantum state control. This is also research in progress. And here you see you would have sub-second entanglement times, and this could be a viable way on Earth to actually do such experiments. Okay, so summary being, this is where we are today. This is where we are going at the moment, and hopefully one day we can even reach a regime where we can overlap that. But I'm really very confident that with the methods that have been developed now over the last 10, 15 years, we have now a way towards such a regime. I think it's super exciting. Also, if you put it in a larger context, so if you look at experiments at the interface between quantum physics and gravity over the last almost 60 years now, so it started out, the first phase was really the proof of concept experiments to show gravitational coupling to quantum systems. The second phase was improving precision by bringing in atom interferometry, cold neutrons, optical clocks, and so on, and really allowing now for precision measurements of Newtonian physics and of GR. And now we are actually entering a regime of extreme matter waves, so masses that are so large that maybe at some point we can also exploit their source mass character. We have optical lattice clocks that boost the precision of timing by another couple of orders of magnitudes. So we enter now a regime where we can look at experimental constraints for dark energy, for dark matter, analog gravity, analog quantum gravity. We can possibly test for suggestions that people have there with respect to gravitational decoherence. So actually this would be sort of new physics. And all the way down to looking for low energy constraints of actual quantum gravity theories, or looking for gravitation-induced entanglement. So I think this here is really a completely new domain that is being opened right now through essentially, I would say, interfacing modern quantum physics experiments, so really quantum technology developments with our new insights in the interface between quantum physics and gravity. Okay, so with this I end. I thank you very much for your attention and leave you with a piece of advice for going home. Thanks a lot.
So one thing that you didn't mention is the possibility of using quantum technology for building better gravitational wave detectors, which is something that's connecting almost directly to what you said. But
yes,
yeah,
so thanks, Roberto. This is one of the slides that I jumped over simply because I felt I was running out of time. It was well felt. So here's essentially. The slide is quantum enhancing gravitational wave detection. And this is really a very exciting development. So you know about gravitational waves, but the question is, can we improve further the current detectors, and can we use quantum physics to do so? The answer is yes. So a very easy thing is using so-called squeezed light. So basically where you reduce certain noise in your laser beam. In that case, you can start with reducing phase noise. So reduce then the phase variance in the outcome of your interferometric measurement, and then basically here improve on the sensitivity of your interferometer. This is only one thing. It turns out if you want to reduce the whole curve here further, you need to generate something called frequency-dependent squeezing. So you have to rotate actually this squeezing ellipse in phase space depending on the frequency that you probe. These are experiments that are ongoing. There's a group at MIT, Nerges Mavalwala and others, who built basically you need very long cavities such that the delay of the light propagating in the cavity introduces then this rotation. There are groups at Virgo, so Antoine Heitmann and his team are working on such large cavities for producing the same. And then in addition to these squeezing approaches, you can even go beyond that, and you can completely eliminate back action, for example, in such systems. There are so-called quantum non-demolition measurements that allow you to basically enter a regime that is even better in performance than with the squeezed light sources. That requires, however, at the moment, still to reduce further the actual noise, the classical noise in the interferometer. So there's right now, this is the noise performance of the current advanced LIGO configuration. And one of let's say, the biggest classical noise source right now is really the Brownian motion of the mirror surface. So you have like, you have a 20 kilo mirror separated to another mirror by 4 kilometers. And the limitation of the thing is really, it's the thermal motion of the 6 micron thick coating on top of these mirrors. This is actually the limiting factor. And it turns out there are some ideas, actually we have worked on some ideas how to reduce this thermal noise further by using different material systems. And this is something that is currently tested in the 10-meter prototype gravitational wave detector. And this will be required in order to then do full-blown QND measurement schemes for that. But that is actually becoming quite a big effort within the gravitational wave community, establishing actually quantum measurements in order to improve on the measurement performance, sensitivity.
But I also had in mind designing new classes of detectors. I mean, not just improving on the interferometers, but I mean, trying to find some way that high precision that's been achieved to design other detectors, which are not just the interferometers, usual interferometers. I mean, I know that there are ideas.
I see. Okay. Well, okay. I mean, there are. Okay. Well, so I could just go to the next slide.
Hasn't been prepared.
I like that. I paid him a lot of beers yesterday to do that today. So there are a couple of proposals out there which are quite nice. So I like them very much. So this is actually Keith Schwab's group, who just have superfluid helium in a container. And essentially what that is a capacitor with a superfluid dielectric inside that can be moving. Okay? Well, you connect that capacitor also to a coil, and then you have an LC circuit, so you can very sensitively read it out. But the point is now what you have is a high Q oscillator that is sensitive to a very specific frequency. So that means if you would have now a gravitational wave at a very specific frequency, you could pick that up. So this is a proposal for a narrow band gravitational wave detector. It's not so uninteresting, because you could actually think of having a whole battery of these things, so to increase the bandwidth, and who knows. Although right now this is still high frequency regime and so on and so on. So, but the numbers are comparable. Then there has been proposals from some groups in the US to use optical lattice clocks as gravitational wave detectors. They actually suggest a satellite-based platform. I don't know if they analyze the situation on Earth, so it might not be suited for Earth, because this is targeted towards the low frequency regime, which can only make sense isolation-wise on space. And then, of course, there are atom interferometry proposals, and these are essentially the groups by Mark Kasevich and Philippe Bouillet, who are trying to trying to show that the performance of atom interferometers is at least similar to what people have at LIGO. Yeah.
More questions?
Yes, so you mentioned dark energy. I'm just curious, what can you do with this test about dark energy?
So the main point about that is that almost all of these dark energy scenarios, theories, do have consequences also on other energy scales. So the art is actually finding them, right?
So you're looking for extra scalar forces, extra scalar fields?
Yeah, so for example, you look at, you ask the question, okay, now I have my experiment, I have a very, for example, I have a particle levitated inside a cavity. What happens now? So what if now in my interaction of the particle with the cavity field and so on, I add now this additional scalar force, right? Is there anything in the behavior, if I now perform a set of quantum operations in a particle, would I be sensitive to some coupling, right? So this is always the underlying idea of these experiments. So you try to find some coupling to some states or some dynamics of the system, and then the measurements that you do are normally the null measurements. So within the error bar of your experiment, you typically don't measure anything, but still the magnitude of the error bar then provides you with a bound on some of the parameters for these models.
Are these bounds comparable to those coming from solar system experiments and so on? The ones that you can get from these experiments?
Yeah, I don't know. I don't have these graphs now here, but normally, so you know, typically there are these graphs where you have at least where you plot one free parameter versus the other free parameter, and you see which domains are actually ruled out. And so the solar system based and beyond experiments, they typically cover the domain of large distances, and the table of experiments cover the domain of small distances. Right? So in that way, they are complementary because they can address different areas in this parameter diagram. But they also have reasons of overlaps.
Any further questions?
So one question for the future. So you want these two streams to connect and start proving quantum gravity directly? What are your expectations on the timescales?
Yeah, thanks for the question. So so we are not proving quantum gravity. I would even say we're not even testing quantum gravity. What we are, so if one, so let's say one can at some point down in the future perform such an experiment. What does one learn? So what such an experiment excludes is the possibility for a description based purely on classical gravitational fields. So there's no way that I can generate entanglement while maintaining that the source mass would create one fixed spacetime. So in that way, what such an experiment probes is a quantum aspect of the gravitational field. It does not, in the strict sense, probe quantum gravity, because normally we attribute to quantum gravity the necessity to quantize the gravitational field. And quantizing means in that case that you have transverse field modes which you then quantize. The problem, the way it's cast here, only requires the longitudinal field components. They don't need to be quantized. So in other words, for such an experiment to understand, you don't need gravitons. However, you do need the concept of a metric inner superposition. Yeah?
So you are quantizing the space-time in which the system resides? Or?
Yeah, I have a problem using the word quantizing. No, the only thing, so basically, let me do it historically. So that's why I also put up Feynman's quote. Feynman was very, let's say, had a very simple definition of quantization. He also said that, if you read through the whole transcript, he said look, in order to describe such an experiment, I have to put a probability amplitude to the field. And if I have to put a probability amplitude to a field, this is what I call quantization of a field. This is what he said. And I think this is a too loose way of speaking about it, but if you're fine with this definition of quantization, then yes. But I think it's stretching too much. So one definitely probes a quantum aspect of the field, but not the necessity of gravitons. It's like if you do such an experiment with charges and Coulomb interaction, then describing this experiment does not necessitate quantization of the electromagnetic field, in the sense that you need photons to be exchanged. But again, you need the notion of the field being in a superposition.
And again, what will be the time scale you will expect? Tens years?
So I still want to be alive. And, yeah, no, it's always hard to say. I mean, again, the last 10 years were amazing. So really, this whole field emanated out of nothing, and within 10 years, we have really basically pushed it to these regimes. So I don't know, give it another 10 years, and let's see where we are.
And for gravitons?
There's no way.
Okay.
No. If you do the numbers, I mean, you just need to take the fields to perturbation theory and an effective quantum field theory. We are lacking another, at least experimentally, another 20 orders of magnitude in order to become sensitive to the second order effects. So, for example, what would be the next effect that you would want to see? You entangle the two with each other, right? So you see entanglement between the two masses. But if you now, then the next perturbation would be you take into account the field degree of freedom. So you would actually also become entangled with the field. So that means that the entanglement only of the two center of mass positions would actually decay. So you would have a genuine, let's say, three-partite entanglement if you want. But because of the interaction with the field degrees of freedom, you would start to see decaying entanglement. But this probing the field on that level, again, requires clocks that are sensitive, need improvement by another 20 orders of magnitude. That's all it's there. You can do the numbers. Say again?
You want to get to the Planck time?
No, it's still above that, I think. I think it's still above that. Yeah. What is Planck time?
Minus 44 seconds.
Yeah, no, it's still above that.
More questions? No, let's thank Markus again for a wonderful talk.